Thanks, Shweta, for the introduction, and to the organizers as well for the opportunity to speak at this seminar series. My talk today is based on this paper that appeared on the archive a couple of weeks ago with Yishen Du, Jung Nguyen, and Dam Sun. So the motivation behind our work is comes from the study of fractons, which has been blowing up in the recent years. For those of you who don't know, fractons are these exotic phases of matter, in particular characterized by excitations that have restricted mobility. There are three types of these classes of these excitations. One can have fractons that are completely immobile, for instance, metaphorically, like the cargo ship stuck in the Suez Canal, although as of yesterday, people luckily have figured out a way to supply the energy cost to move it without creating a ship and an anti-ship. One can have particle excitations that are restricted to move along a single line. These are called line-ons, and similarly restricted to move along a plane in 3D space. These are called plane-ons. One very interesting feature about, an interesting and non-trivial feature about these systems is that the ground state degeneracy of the lattice models that are usually considered is very large and grows exponentially in the system size. In particular, in a thermodynamic limit or in the continuum limit, it's exactly infinite. These systems are also characterized by exotic conservation laws, instead of the usual conservation laws where you have some charge density, whose time derivative is given by the divergence of a vector current. You can have additional indices showing up on the densities and the currents. Originally, these models were discovered in the context of error correction codes, but they've also found applications to various different fields of physics, in particular, including elasticity theory. And I will point out these two review articles that contain many of the references that are relevant for this. Okay, so moving on to higher rank gauge theory. Higher rank gauge theory is basically a simple class of theories that captures some aspects of fractonic phases, even though not all. In particular, the fact that the excitations have restricted mobility. One constructs higher rank gauge theory by starting with a tensor gauge multiplet that consists of the usual electrostatic potential A0, but instead of a vector potential, one can have a tensor potential or something with higher indices. For this slide, I'll mainly focus on the simplest version of it, which is scalar charge theory. So you have a tensor gauge potential and correspondingly a tensor electric field that's symmetric in both indices. One postulates a Gauss's law, a generalization of Gauss's law for this tensor electric field. In the context of scalar charge theory, we have the double divergence of E is equal to some matter density rho. In a Hamiltonian formalism, this implies that Aij transforms under a gauge transformation by two derivatives of a scalar function. Now, from this Gauss's law, one can derive conserved quantities. In particular, naturally, the total charge, as always, will be conserved, but also the total dipole moment, which is the integral of x times rho in flat space, is also conserved. This has very non-trivial implications, which is the fact that isolated charges are now immobile because if they move, their dipole moment will change, which is not allowed by our conservation laws. The theory I'm going to focus on for this talk is called the traceless scalar charge theory, where in addition to what we saw on the previous slide, we also have a trace constraint, which sets the trace of E to 0. And we'll be working in the traceless gauge where the trace of A is simultaneously also 0. Gauss's law once again generates a gauge transformation, which now looks like this, where we have this additional Laplacian transformation. And also for we also have a gauge transformation for A0, where the variation is just lambda dot. One can derive field strengths for this, the electric field and the magnetic field, which is given by this curl with respect to one index of the tensor gauge potential, anti-symmetrized in the free indices. And from there, we can write down gauge invariant Lagrangian terms, for instance, a generalization of the Maxwell term, which is E squared minus B squared, or a generalization of the Chen-Simons term, which only exists in 2+1 dimensions and is gauge invariant up to a total derivative, which implies that the coefficient has to be quantized. For the rest of this, for most of this talk, I will be focusing on 2+1 dimensions. So,
sorry, I have a question. Can you go back to the previous slide? Yeah. Can you say? Oh, sorry. The next.
Yeah.
Maybe the current. Yeah. Can you say what are the mass dimension of your field strengths? And gauge fields.
Right. Okay. So naturally that depends on the dimension. The electric field has a mass dimension. So let me start off from the beginning. The tensor gauge field Aij has dimensions of inverse length squared, so mass dimension 2.
Right.
And the electric field goes as its time derivative. Time derivative also has mass dimension 2 in a non-relativistic scaling. So the electric field scales as mass to the 4th.
For electric field, I thought it scales like dimension 3 because it has one more derivative compared to Aij.
It's the time derivative of Aij, or equivalently di dj a0. And we're working in a non-relativistic scaling where time scales as length squared.
And H has dimension 4.
Yeah, exactly.
But then A0 Hij, does it have dimension 6 in your counting?
Yes, that is correct.
But if you are in 2+1, do you need a dimension for coefficient in front of the Chern-Simons term?
In 2+1D, yes, from the scaling, you would need a dimension for coefficient.
Oh, so the level of your Chern-Simons is dimensionful.
Yes.
So why did you say that it's quantized?
Oh, one would expect that because there's a gauge invariance up to a total derivative.
Well, I don't agree with the reasoning, but independent of that, since it's dimensionful, in which units is it going to be quantized? Only dimensionless quantities can be.
Right. Sorry, I should take that back. I need to think about that more carefully.
Okay, thank you.
Yeah. All right. So one can couple these gauge fields to matter fields, and in particular for the rest of, for most of this talk, we're going to be working with gauge fields that are background and non-dynamical instead of the dynamical gauge field. So we won't be concerned with the kinetic term in the action, and only think about these gauge fields as backgrounds. We can couple this to to a scalar charge density rho and a tensor current Jij via this minimal coupling. And from there derive a conservation law for rho and Jij, which is that the time derivative of the density goes as the double divergence of this tensor current, and also that the trace of this tensor current is 0. And from these equations, we can find out what the conserved charges look like. First of all, we have the usual total charge and the total dipole moment as before, but the traceless constraint adds another conserved quantity, which is the specific component of the multipole moment, integral x squared rho. Conservation of the dipole moment implies that isolated charges cannot move, but the conservation of this multipole moment implies that dipoles are not free to move. They can only move perpendicular to their dipole moment. Okay, so now that I have the setup of this the background necessary for the talk, here's the outline. I'll start by first describing a bottom-up procedure to construct these, to upgrade this traceless gauge symmetry to volume-preserving diffeomorphisms. I'll introduce a gauge multiplet for volume-preserving diffeomorphisms in particular, and show how in specific situations, the long wavelength GMP algebra, also known as the little w infinity algebra, can be obtained. Part 2 will be a top-down approach instead, where the same volume-preserving diffeomorphism invariant multiplet and the appropriate couplings will be derived starting from a theory that has a U1 gauge symmetry and non-relativistic diffeomorphism invariance. In particular, this will reveal a connection to lowest Landau level physics, which will allow us to realize this symmetry in various physical systems. And it'll also allow us to generalize this to 3+1 dimensions. And finally, I will talk about the various physical systems this is realized in. For instance, composite fermions in quantum Hall systems, crystals on the lowest Landau level. Both of these are, oh, I'm sorry, was there a question?
I had a naive question. If we go back to your action, this seems like an analog of there's one analogy to the relativistic theory, which is your analog of the Yang-Mills term seems irrelevant if the Chern-Simons terms are present, right? It has scaling dimension. Is there any reason we have to talk about it if you're going to go to the long wavelength limit?
So I am not going to talk about the dynamics of this gauge field at all. I'm going to be treating them as background fields. So I'm more concerned with the matter sector and how it couples to this volume preserving diffeomorphism invariant multiplet. Does that answer your question?
Yes, thank you.
Okay, thanks. Right. So for the realization in physical systems, this connection to lowest Landau level physics implies that we'll observe this volume preserving diffeomorphism invariance in a system of composite fermions in quantum Hall states, crystals on the lowest Landau level, where it's naturally obtained by virtue of there being a lowest Landau level, but also a hidden symmetry in ferromagnets, in particular related to the mobility of skyrmions. Okay, so starting with part one of my talk. So we'll first begin by sort of doing a field redefinition. Instead of working with this tensor gauge field AJK, we'll define a symmetric traceless tensor Hij by multiplying it with an epsilon tensor and symmetrizing. Now the gauge transformation for Hij looks like a linearized diffeomorphism for a metric, where the translation xi, the coordinate transformation xi, is defined as the curl of the scalar lambda with some coefficient L squared. L takes dimension length. However, by this definition, the xi has to be divergenceless. So in particular, we're looking not at any diffeomorphism, we're looking at volume preserving diffeomorphisms. For now, I'm only considering flat space. So from here, it's easy to sort of generalize to a nonlinear multiplet where instead of A0 and Hij, we consider a full metric, Gij. The metric will then transform as a rank 2 tensor under these non-relativistic diffeomorphisms, but Xi now still is defined as the curl of the scalar lambda. The transformation of A0 is not trivial.
Are you doing the gauge transformation or are you doing the coordinate transformation?
So I'm saying that the gauge transformation for A looks like a coordinate transformation for this field Hij that I've just defined.
But do you also shift the coordinate x or not?
Yes, we do.
So then it's not a gauge transformation if you shift x.
Yeah. Yeah.
When you perform a coordinate transformation on the gauge field, you have two effects. One is that because of the index it shifts, but also because the argument shifts.
Right. But in a gauge transformation, it's just the coordinates aren't changing.
That's right.
So this is a coupled, and we have to have some tactic. So let's try not to do that here, but based on a merit of each case.
Sorry, I think I missed, what was that?
A follow-up comment?
Yeah. So we are, let's see. So the transformation of A is a gauge transformation, which results in a transformation of Hij that looks like a volume preserving diffeomorphism, a linearized volume preserving diffeomorphism. Yeah, so we sort of, our generalization relies on interpreting this as a coordinate transformation as opposed to a gauge transformation.
So for example, you had also some matter fields that appear in rho. Rho depends on some dynamical fields. Are their coordinates also transformed or not? Right, it was rho of x.
Right.
Transformed?
Yes, their coordinates are transformed.
But that's not a symmetry of your problem.
Right. It's simply a volume preserving diffeomorphism, but which at a linear level results in this gauge symmetry, this tensor gauge symmetry. So maybe the reverse will be more clear. So you start off by performing a volume preserving diffeomorphism on your theory, and then linearize it, and one can find a conservation equation for the charge density and the stress tensor that looks like this dipole symmetry. That looks like this higher rank symmetry conservation law. Does that answer your question?
Not quite, but we should continue. I don't want to slow you down.
Okay. So the transformation for A0 here is still non-trivial because volume preserving diffeomorphisms do not commute with one another, unlike the higher rank gauge symmetry transformations. In particular, the commutator of true transformations looks like a transformation parametrized by this spatial Poisson bracket of the two parameters, where alpha comma beta is given by epsilon ij di alpha dj beta. And one can see that a transformation of A0, one can correct the transformation of A0 with this Poisson bracket term, which is in fact just a Lie derivative of A0 with respect to Xi, that this now agrees with this non-abelian nature. So our generalization of this traceless gauge symmetry is in fact a non-abelian symmetry. I should note that the connection between higher rank symmetry and gravitational physics was first noted in this paper by Xu in 2006. And in particular, the connection with volume preserving diffeomorphisms was also noted by this paper by Gromov in a paper in 2017. However, they mainly focused on the transformation of the metric and didn't have A0. And also in Gromov's paper, this metric is supposed to be an emergent dynamical field, whereas we're considering an explicit background metric in our case. Okay, so from this, we can find that under certain conditions, the matter sector must obey the GMP algebra. So let's say we start with some matter theory and couple it to this gauge multiplet A0 comma Gij with some coupling term. In particular, it's important here that this coupling does not involve any time derivatives of the fields, so that Gauss's law, first of all, remains the same. Second of all, does not have any time derivatives, so that it can still be thought of as a constraint that generates these gauge transformations. So now, Gauss's law relates the conjugate to Aij, to the matter charge density rho. The electric field generates gauge transformations in the gauge sector. The charge density then generates gauge transformations in the charge sector. And one finds that the non-commutativity of diffeomorphisms then implies that the charge density must obey the long wavelength GMP algebra. Okay, so that's part one of my talk. This was just a simple sort of upgradation of this traceless gauge symmetry into a multiplet for volume preserving diffeomorphisms. In part two, I'll talk about this top-down approach where I start from a U1 cross non-relativistic diffeomorphisms and reduce it to volume preserved. Okay.
So, Umang, can I ask a question?
Sure.
For the GMP algebra, you wrote down the linearized version. Does that have to do with your restriction of volume preserving diffeomorphisms to only like linearized volume preserving diffeomorphisms?
No, this is for the full nonlinear volume preserving diffeomorphisms. In fact, if it was linearized, the symmetry would be abelian, so there wouldn't be any commutator.
Oh, right. I see.
Yeah. So the full volume preserving diffeomorphism algebra results in just a long wavelength GMP algebra.
I see. And I guess can you talk about why we only see the linearized version instead of the full GMP algebra? Sorry, the long wavelength version? Because we're doing like some field theory and we can't see like short wavelength things?
Sort of, but also volume preserving diffeomorphisms don't. The capital W infinity algebra, which is the full GMP algebra, is a deformation of volume preserving diffeomorphisms. It's not volume preserving diffeomorphisms. So one shouldn't expect to see the full GMP algebra in a theory that only has volume preserving diffeomorphisms, unless you deform it in some way.
I see. Thank you.
All right. So in this, for this case, we'll start off with a set of massless Schrodinger particles coupled to a U1 gauge field and a spatial metric. This system will be invariant under time-dependent spatial diffeomorphisms. The reason we want massless Schrodinger particles is that if m is not equal to 0, the spatial components of the gauge field does not transform like a one form. There's an additional term proportional to m times c dot. Setting m to 0 gets rid of that term. We now fix a magnetic field, a non-zero magnetic field, which defines a natural volume form for the theory. Hence, it breaks these the diffeomorphism group down to volume-preserving diffeomorphisms. In particular, the massless limit implies that we are restricted to the lowest Landau level because all the higher Landau levels have infinite energy.
Is the metric classical or quantum? And the same is about a mu. Are these fields background fields or do they fluctuate?
These are background fields. A mu and Gij are background fields.
So, but the diffeomorphism group acts on the background fields.
Yes.
So the system for in flat space and with A mu equals 0, does it have any diffeomorphism symmetry or not?
So in flat space with A mu equal to 0.
So you turn off all the background. So the metric is flat, space is non-compact, and A mu is 0.
Then there is no diffeomorphism symmetry. It's only when we turn on these fields and think of them as background fields and allow them to transform as background fields do we have this sort of diffeomorphism symmetry. It's not exactly a symmetry because the background fields are transforming under it.
So the system without any background field, does it have any conserved charge or all the other consequences of symmetry or not?
Not that we're considering here.
But then if you couple it to the metric and you let the metric transform, it's invariant on the full coordinate transformation, not only the area preserving, the volume preserving ones.
Right, but when you fix B, then any transformation that doesn't preserve volume will change B. So we want B to remain the same. For instance, in some experimental setup with a quantum Hall system, B is something that's being controlled by the observer.
B is a background, right? It's the same as A mu.
Yeah.
Okay, so if you let your symmetry act on the background, both in Gij and A mu, then you have the full coordinate transformation.
Right. But we also want to fix B. So let's say fixing B is taken as a postulate where we're allowing A mu and Gij to transform because those are treated as probe fields. But B is something that's fixed by the experimental setup. They're treated as sources for the matter in the theory. Does that answer your question?
Not quite. I think what you're saying is that you fix some background fields, but not others. But if you allow all the background fields to transform, then you have much bigger symmetry.
Yes.
What I don't understand is why should you fix some? Once you allow the background and you allow the backgrounds to transform, I don't see the rationale of fixing some of the background, but not something else.
So the point of fixing B but not everything else is because A mu and Gij varying with respect to them gives us correlation functions of the matter sector, for instance, the density correlation functions, stress tensor correlation functions. So we do want to allow them to vary, and their transformations allows us to constrain the matter system. The reason I want to fix B is because in general, it may be very difficult to fully couple the system to a background A mu and Gij. The transformations might look very complicated. It might suffice to couple it only to A0 and Gij. And I want to introduce how that can happen, assuming that you can couple it to a full U1 and non-relativistic diffeomorphism invariant background fields.
Okay.
Okay, yeah, maybe I can move on and we can continue that discussion later. Right, so fixing this B breaks the diffeomorphism group down to volume-preserving diffeomorphisms. The massless limit implies that we're restricted to the lowest Landau level because all the higher Landau levels have infinite energy. Now, delta AI under a diffeomorphism characterized by some parameter C, which is the curl of lambda, turns out to be a total derivative of some function and can hence be canceled by a U1 transformation. But this U1 transformation applies to A0 as well. So from this, we obtain the same transformation laws that we had on the previous slide, which I'll flash here for a sec, namely that Gij transforms as a rank 2 tensor, and A0 transforms with this lambda dot minus this Poisson bracket term. Immediately, there are some corollaries to this. The first thing being that
when you say you're fixing B, you're really fixing all the spatial A's, right? You're saying you're treating A0 and G as your background fields that transform in this Booleanic symmetry, but AI and AJ are completely fixed.
Exactly.
Thank you.
Because the transformation of that can indeed be canceled by a U1 transformation. Okay, so the first corollary to this is that the lowest Landau level naturally realizes a dipole conservation law, where the time derivative of rho is given by two derivatives acting on the stress tensor, written here in schematic notation by suppressing indices. And this is, in fact, it's very easy to see how this can be obtained in the lowest Landau level, starting simply from the conservation equation for the charge density and the conservation equation for momentum density in the presence of an external magnetic field. However, because we're in the lowest Landau level, in a Galilean invariant system, the momentum density is proportional to the mass, which is set to 0. Therefore, that equation simply expresses the charge current in terms of a derivative of the stress tensor, and from there we can actually obtain this this equation directly. A second corollary is that when you have a theory coupled to a U1 and a U1 gauge field and a spatial metric, one can write down a when Z term that usually governs various topological responses of the matter sector. And this, in fact, when linearized, is just the Chern-Simons term, which can be written as A0R minus epsilon HH dot schematically. And what this also implies is that the equivalence of the shift of a quantum Hall state, which is a coefficient of this first term, and the Hall viscosity of the quantum Hall state, which is this coefficient of the second term, is in fact a consequence of this generalized higher rank symmetry, or of volume preserving diffeomorphism invariance. Okay, so this 2D perspective can be easily generalized to 3 dimensions. In particular, instead of a U1 vector U1 gauge field, we start with a Karl-Bramon field, which is an antisymmetric rank 2 tensor. Its gauge invariance under a similar transformation where the gauge parameter now is vector valued, has a vector index, and we fix the spatial curvature of this field, which is just the antisymmetrized derivative, to be proportional to some L to the -3 times the epsilon tensor. Once again, this breaks volume preserving diffeomorphisms in 3+1D down, diffeomorphisms in 3+1D down to volume preserving diffeomorphisms, and that are now characterized by a coordinate transformation that is given by the curl of a vector field lambda instead of a scalar field as we had before. Once again, we'll find that the variation of the spatial components can be canceled by a gauge transformation. This gauge transformation also acts on B0I, and from there we find this volume preserving diffeomorphism invariant multiplet, which consists of this spatial vector B0I and the spatial metric Gij. I will put up the transformations for both of those here for convenience, but the technical details of these equations aren't important.
Sorry, I have a quick question. What's the relation between alpha in the second line and lambda that are below?
So alpha is different from lambda, unless you're specifically acting on this gauge transformation that cancels the volume preserving diffeomorphism. Over here, we're basically looking at diffeomorphisms that are volume preserving, so they're parametrized by this lambda. And from there, one can find out that delta Bij does in fact look like a d alpha of this form and equate alpha to some function of lambda.
Okay.
Could you go back actually to the previous slide? I'm a little confused about the analogies with quantum Hall just because of this earlier point that was made that the Hall, the coefficient of the Chern-Simons term in this Z equals 2 theory seems not to be quantized.
Mm-hmm.
Am I supposed to have intuition that this is like a quantum Hall system for non-relativistic particles, or what's the intuition I should have here?
So the intuition here is simply so you have these when Z terms in non-relativistic quantum Hall systems that characterize response to a metric perturbation or to a gauge field perturbation. The linear response in particular. The idea here is simply that this term, when linearized, is simply the Chern-Simons term, the higher rank Chern-Simons term, when re-expressed in terms of these gauge fields. Does that answer your question?
I guess so.
Okay, so I'll just pause here for 1 second to sort of illustrate the how one obtains this volume-preserving diffeomorphism invariant multiplet. The weird thing about it is that this A0 in the 2+1 dimensional case is shared between a U1 multiplet and the volume-preserving diffeomorphism invariant multiplet because we obtained A0 and Gij by fixing AI. And similarly for the 3+1 dimensional case as well. One can still turn AI back on and couple it, add some fluctuation delta AI to it as another source field and couple it back to the theory, but we won't be doing it for the purpose of this talk. So now that we have a 3+1 dimensional version of this theory, we can talk about conservation laws. B0I must couple to a vector charge density. Gij obviously couples to a stress tensor, and the conservation law looks like this vector conservation law where the time derivative of the charge density is given by 2 derivatives acting on the stress tensor. The charge density is also divergenceless. In particular, if we postulate that this Ji is non-zero in only a finite region, it can be written as a curl of some mu. One way to think about this is an analogy that is potentially helpful is that mu is some sort of magnetic moment density, and J then would be a magnetization current for the system. In the case of J being non-zero only in a finite region, there are 2 conserved quantities. One is this integral of mu, which is the total magnetic moment. And the other one, which can also be written as integral of x cross J, and the other one is the integral of x cross mu. And here's an illustration to sort of help visualize mu being the magnetic moment density of, say, a solenoid, J being a magnetization current, and then integral of mu lies in this direction. In particular, this second conserved quantity restricts the movement of whatever loop excitation you have to be parallel to the magnetic moment. So this loop of J can only move parallel to integral mu and not perpendicular to it. So we do observe this sort of restricted mobility that is characteristic of fractonic systems.
If you said you have these volume preserving diffeomorphisms, so then you have curvature in space. Do those integrals still make sense in the presence of spatial curvature?
So we're specifically looking at flat space for this talk. We haven't given too much thought to how this would act when you do have spatial curvature. But naturally, these integrals directly don't make sense. But I'm not sure if there's any generalization of this to spatial curvature, but at the very least, this local form does make sense.
I see. Wait, what were the volume preserving diffeomorphisms acting on then, if it's not the metric?
They are acting on the metric.
Then doesn't that lead to some sort of curvature?
Well, it's a coordinate transformation. The curvature, if you start off with a flat space.
Oh, it's just a trivial gauge transformation, you're saying?
Yeah, exactly.
Okay, thank you.
All right.
Just to be clear, your space is flat and your metric is, even if it's non-trivial, it still has no curvature or anything.
Yeah.
So it's a pure coordinate transformation.
Yeah.
but then, so what is the remaining cast of characters? How many fields how many background fields do you have?
The components of the metric and A0.
But the component of the metric are constrained such that the local curvature is 0.
Yes, that's correct.
So that doesn't leave many components. In 3+1 dimensions, there are 4 components.
Right.
Because there is a coordinate transformation that makes the metric trivial.
Right.
And then how many transformations do you have from the volume preserving?
So in 3+1 dimensions, it would be characterized by 3 components of the vector lambda.
Okay.
I think there might be a confusion here. The conservation laws that you have written down are written as a Watt through the Watt identity, and then you put the space to flat. So these, but one can define the theory in any curve metric. One can couple the theory to curve background.
Right. Yeah. So in particular, I'm focusing on flat space here after computing all these Watt identities in a general background.
Excuse me, I have a related question.
Mm-hmm.
And so, in general, the volume preserving transformation will change the Gij in general.
Mm-hmm.
Maybe there's some special volume preserving transformation which do not change Gij. Whether it is those special one which give you a conservation law, like this dipole conservation, things like that.
Ones that
to be real, this kind of volume preserving transformation will be real, like a symmetry, because they do not change Gij.
Mm-hmm.
Lagrangian environment.
Right. I'm not sure, actually. I haven't thought about that. Okay. Yeah, at a linearized level, for instance, there would be those transformations for which the symmetrized derivative of Xi, the coordinate transformation, is 0. But yeah, I need to think about that more in order to answer your question.
For example, in the linear transformation, the transform, like there are two derivatives of Xi. If Xi are linear, then there's nothing. So that's give rise to conservation law.
Right. Perhaps.
Yeah. Okay.
Yeah, that makes sense. All right. So moving on to part 3, we'll demonstrate how various already known physical systems can in fact be coupled to this volume preserving diffeomorphism gauge multiplet, starting with composite fermions, crystals on the lowest Landau level, and in particular, I'll talk about ferromagnets having this sort of hidden transformation invariance as well. So composite fermions in a nutshell are basically electrons on the lowest Landau level that are coupled with magnetic fluxes. So you have the total magnetic field, you can imagine in some approximations, splits up into fluxes and attaches themselves to these electrons, and you get a composite fermion in that way. These are pseudoparticle excitations in the various quantum Hall states. In particular, we're going to be interested in the metallic states at even denominator filling on the lowest Landau. And it's a known fact that quasi-particles for these fillings, like half, 1/4, etc., are electrically neutral, but do have an electric dipole moment. One example of an action that such a system would have would be just a Schrodinger action for a scalar fermion, composite fermion psi with a single time derivative term and a spatial derivative, quadratic spatial derivative. Generalizing this term in the presence of a metric is simple. You just replace what would have been a delta ij in the numerator here with a gij. But this time derivative is not invariant under the transformation that I mentioned. Therefore, one needs to add a compensating term that looks like this. And one can check that this compensating term cancels the transformation of this first term. So this object in blue is the electric field, which means that this object in green can be interpreted as the dipole moment of the system of composite fermions. So you get this sort of dipole coupling E dot D. However, notice that because of this epsilon ij, the dipole moment is in fact perpendicular to the momentum of these composite fermions. And that's the statement I want to make here. As we saw in one of the previous slides, composite fermions are in fact dipoles of this higher rank symmetry, whose momentum is constrained to be perpendicular to the dipole moment. So they can only move perpendicular to the dipole moment and not parallel to them. There's another way of seeing why such a coupling should exist, which is through Newton-Cartan invariance. The prescription for that is to take a time derivative term and replace it with u dot d mu, where u is some d plus one dimensional velocity that picks a preferred frame in our non-relativistic spacetime. In our case, we have a natural choice for u, which is 1 comma this vector given by epsilon ij times the electric field. And with this prescription, we obtain this action back. Another example is that of a Wigner crystal on the lowest Landau level. I will remind you, Wigner crystals are obtained from are these quantum Hall states at really small filling where the electrons are very far away from each other. They end up crystallizing into a solid. In particular, it's important here that on the lowest Landau level, spacetime is non-commutative. The commutator is given by minus I L squared, where L squared is 1 over b, the magnetic length, the square of the magnetic length. The degrees of freedom in this case are these coordinates frozen into the solid, capital XA. The displacement, for instance, of any particular location of the solid would be given by the difference between the background coordinates and these solid coordinates. Under a volume preserving transformation, XA transform as scalars, so simply by a Lie derivative. The non-commutativity of spacetime implies that the action must contain a Berry phase term, which looks like XA times the time derivative of XB with an epsilon AB. Now, this term is not invariant under volume preserving diffeomorphisms. It transforms as lambda dot times dx dx with indices suppressed, which allows us to add a compensating term, which looks very similar to the term that we had before, with just the derivative on A0 instead moved over to the right. So this is also a sort of dipole coupling where the electric field couples to some sort of dipole moment and results in similar constraints on the mobility. A third system is that of a vortex crystal in the lowest Landau level. Something like this is obtained, for instance, in a rotating Bose superfluid, where you take a superfluid and rotate it with a very high angular velocity. The angular velocity behaves like a magnetic field for the superfluid, for which I will refer you to these papers. And we end up getting a vortex crystal in the lowest Landau level. Once again, the degrees of freedom are the usual lattice coordinates I defined in the previous slide, but you also have a superfluid phonon in the dual description defined by a emergent gauge field A mu, and we'll also add to that a volume preserving diffeomorphism multiplet. A mu now transforms like a standard one form under volume preserving diffeomorphisms. And it is known that X couples to A, but not to the background electromagnetic field. The background electromagnetic field, capital A, only couples to this system through little a via this mixed Schoen-Simons term, ADA. So coupling this to A0 and Gij is simple. One simply rewrites this term in the presence of a fixed magnetic field. So ADA simply is simply equal to this when you set capital B equal to 1 over L squared. And you find this action. Working out the equations of motion for this action, you also find the usual Tkachenko mode with a quadratic dispersion, as one would expect. Finally, to the last example, I'll talk about ferromagnets in 2+1 dimensions. Ferromagnets in 2+1D are defined by an O3 nonlinear sigma model. With a usual quadratic term over here. However, one also needs to add a Wess-Zumino term in an extra dimension parameterized by the coordinate sigma in order to account for the Berry phase of these spins in the continuum limit. NA is an O3 vector that is normalized to be equal to 1. Note in particular that in this case, there is no natural magnetic field or anything that could potentially break diffeomorphisms down to volume preserving diffeomorphisms. So it would be very non-trivial if we were able to couple this to A0 and Gij, which indeed we are able to. Under a volume preserving diffeomorphism, the West-Zumino term is not invariant. In fact, it transforms as an integral that's with an integrand proportional to lambda dot times this thing in the bracket, which is in fact the skyrmion density. Let me remind you, skyrmions are topologically non-trivial configurations in these ferromagnetic systems in nonlinear sigma models that are characterized by a winding of the vector n in the target space. In particular, the skyrmion density is something whose integral is quantized to be an integer and measures this winding. If we choose L squared to be equal to 1 over 4 pi S naught, then A0 we can choose it. We can say that it couples to the skyrmion density, which is appropriately normalized because of our choice of L squared. And now this combination of the Berry phase term, the West-Zumino term, and SA0 is invariant under volume preserving diffeomorphisms. The nonlinear sigma model term is simply replaced with a metric coupling that looks like this, and we find an action that is invariant under this transformation. So what are the consequences of this for skyrmion mobility? First of all, we can conclude that skyrmions behave like particles in an effective magnetic field, where B effective is given by this value minus 4 pi S naught. This is not a new fact. It's something that was known all the way back in the 1990s. We've just given a reinterpretation of this fact. Secondly, we have a bunch of conserved quantities for these skyrmions, which would be the total winding, which has to be conserved because it's a topologically quantized number, the skyrmion dipole moment, and this particular quadrupole moment of the skyrmion. Once again, this is not new. This was known all the way back in the 90s. And we've just given a reinterpretation of that fact. One can generalize this to 3+1 dimensions as well for the same sigma model. Instead of SA0, we now have a coupling to this time component of the Kalb-Ramond field, where B0i now couples to the time component of a one-form current given by this that is also conserved. So in other words, this time component can be taken to be a vector charge density, which, if it is finite if it is non-zero in a finite region of space, can be written as this curl of some mu. And from there, we also find these two conserved quantities that we had in the 3+1 dimensional case, which is the total magnetization and X cross mu. Again, this is nothing new. This was also first discovered in this 1990s paper by Papanicolaou and Tomaras. And once again, all we've done is given a reinterpretation of this fact. So that's the end of my talk. I'll leave you with this summary slide. Essentially, what we did was promoted this traceless gauge symmetry to volume preserving diffeomorphism invariance, whose multiplet can be thought of as obtained by fixing B and AI to break U1 cross diffs to volume preserving diffeomorphisms. This canonically suggests that this naturally suggests that many examples of such as of these non-trivial conservation laws can indeed be obtained from the Landau level, as lowest Landau level, as we saw. But also we have a hidden symmetry of this type in ferromagnets, which also results in similar mobility constraints. One open question here is that, given that we saw this realization of the classical W infinity algebra, can a similar coupling be deformed into the full the deformed capital W infinity algebra, in particular, perhaps through some sort of non-commutative field theory, because as we saw, there were these Poisson brackets in space appearing frequently, which can potentially be upgraded to a Moyal bracket. That's the end of my talk. Thank you for listening.
Yeah, thanks, Umang, for the wonderful talk. And now we have several minutes for questions. Please unmute yourself to ask a question. Yeah.
Yeah, I have a question. I wonder whether this volume preserving symmetry is always there, or it can be broken by, say, lambda level mixing. For example, in quantum Hall states, when you restrict the first and lowest lambda level, you may have this additional symmetry. But when you have a lambda level mixing,
right,
virtually, whether you still have those symmetry or something is broken.
I think something would be broken because we specifically require. If I go back to this previous slide, we specifically require the Schrodinger particles to be massless. Otherwise, we're not able to go through this procedure and obtain these transformation laws for Gij and A0. So we do need to take the limit where all the higher Landau levels are pushed up to infinity.
Okay, thank you. Yeah, so that's a limit where, yeah, that's in that limit. Okay, thank you.
Yes.
Actually, can I ask something? So, so the dipole conservation here is actually a natural consequence of the relation between the momentum and the dipole
right.
in the magnetic field. So what about higher quadruple, like quadruple conservation? So what is the natural picture for that?
By quadruple conservation, you mean
like x square rho integral, something like that.
Right. So that should also be obtained just from this equation. By dipole conservation law, I meant this particular local equation of the local form of the conservation law. Integrating this with x squared results in the same thing.
Okay, I see. Okay.
Yeah.
Check it. Oh, you go ahead. I can add something.
Yeah. I should say I have suppressed some epsilons over here as well. So there is this sort of traceless aspect of whatever current is obtained on the right. There's just a schematic form to indicate the dependence of the current on the stress tensor.
Okay, I think this looks like conservation of angular momentum in quantum Hall context.
Okay, cool, yeah.
Yeah, actually, there's maybe a related question. Suppose the XY direction is not symmetric, you know, and you somehow break rotation symmetry. Then do you still have this volume preserving diffeomorphism, or you do require this rotation symmetry in quantum Hall context?
It's a good question. Let's see. Yeah, so I would expect that rotations are indeed a part of this. For instance,
okay.
If you take lambda to be linear in X, then the coordinate transformation C is simply a constant.
Okay, yeah. So you do require rotation symmetry, I see. Yeah, there's an experimental consequence because there's some sample which break actual rotation symmetry. So
right. So I wouldn't expect this to apply to, for instance, nematic phases in quantum Hall systems.
Yeah.
Any other question? Okay, if there's no question, let's thank Umang again. And yeah, we'll see everyone next week.
Thank you.